Nawaz. In this lecture we'll do some results on subspace and product topology, but before that let us first recall what do we mean by the subspace topology. So suppose if we are given a topological space, say xt, so this is our topological space, and suppose y is any subset of x. Then if we look at this collection T sub y, which contain all the elements which are obtained by taking the intersection of open sets in x with y, I mean if we take this Ty to be the sub collection of intersection of open sets of x with y, where u is open x, then we proved in last lecture this collection forms a topology on y, and we call this topological space the subspace topology, and this Ty, this y is said to be a subspace of x in that case. Now, so this means if this y and Ty be the subspace on topological space, then an open set say V in an open set V of y is of the form V is u intersection y for some u an open set in x. Now there is this question, how the closed sets in y look like. I mean, does they look like the same as open sets? I mean, is it true that if A is closed set in y, if and only if A is of the form B intersection y, where B is closed in y? Now this is the question in x. Sorry, I mean, does the closed sets in the subspace topology look like this? And the answer is yes, and we will prove this fact in the following lemma. That is, so if we consider a topological space, say xt, so this is our topological space, and we consider y be subspace of x. Then a set, say A is closed in y, if and only if A is equal to B intersection y for some closed subset B of x. So that is what we have to prove. So we'll first assume that A is of this form. So assume that A is equal to B intersection y for some closed set B of y. So we are going to prove this A is closed in y. So we have this space here x, so this is our space x, and we have a subspace y here. And let us suppose this is the subset B. So this is this space y, and this is the subset B, and this is the intersection. I mean, this is A here in this portion. this is B intersection Y. So what we want to prove is closed in Y. So we wish to prove A is closed in Y. Now since this B is closed, so this is not Y, this is X here. Now since B is closed in X, so its complement will be open. So since B is closed in X, B complement in X. So by Cx we mean complement in X. Let us write this down. Complement of B in X. So this is open in X. So if we take the intersection of this set with Y, that will be an open subset of Y. So this implies B complement in X intersection Y. So this has to be an open set in Y, because the open sets in Y are going to look like this. I mean so B complement of X is open in X. So if we take its intersection with Y, then this element will be an element here. So this implies this is open in Y. But if we look at this expression here, so if we look at B complement in X, so that is all the X except this B, and if we take its intersection with Y, then we will get this portion over here. So this shaded portion is, so this is actually when we take complement of B in X and take its intersection with Y, so this is B complement in X and its intersection with Y. But this is same as if we take complement of A in Y. So if we take complement of A in Y, that is going to look like, so if we take complement of A in Y, that will be this set here. So but so one can observe that if I look at this set, which is B complement in X intersection Y, is actually equal to, so this is actually equal to complement of A in Y, i.e. that this is complement of A in Y. Now B complement in X being closed, I mean sorry, this means this is open set in Y, so its complement will be so since so this means now we know that this is an open set in Y, therefore this is open set in Y, and hence its complement is closed in Y. So since So this means A complement in Y is open in Y, and hence it is complement in Y, and hence it is complement in Y, which is equal to A is closed in Y. So this proves one direction. I mean, if we choose A to be equal to this expression here, while B is closed in X, then A will be closed in Y. Now conversely, assume that A is closed in Y. We have to prove A is of the form B intersection Y, where B is closed in X. So we wish to prove A is equal to B intersection Y for some closed set B of X. Now A being closed in Y means its complement is open in Y. So note that A, it is complement in Y is open in Y. Now we know that the open sets in Y are of the form U intersection Y for some open set U of X. So then, by definition of subspace topology, this open set is going to look like U intersection Y for some open set U of X. Now U being open means its complement is closed in X. So now in this situation we are like this. So this is over set X, and this is a subspace, say Y, and this is our closed set A in Y. Now this A is so if we look complement of A, so complement of A is going to look like, I mean, this complement over here, so if we look at this open set U, so if we look complement of A in Y, that is going to be this set. So now this means, so this shaded portion over here, this is A complement in Y, which we assume, I mean A being closed, so this is an open set, and we use the definition of subspace topology. Here we are able to exhibit an open set U in X such that A complement is actually U intersection Y. So this is over U. So this is over U. So if we took U and look at its intersection with Y, that is going to be this set here. So this is U intersection Y. Now U complement being closed, so observe that A is actually, if we take complement of u in x and take its intersection with y, that is over A. So what we have to do, we have to take the complement of u in x. So the complement of u in x is this portion. So if we look at u complement in x and take its intersection with y, so this is over y over here, so the intersection will be in this portion over here, which is A. Now note here this u is open in x, and hence u complement in x is closed in y, and that means this closed set A in y is of the form a closed set in x intersection with y. So since u complement of x is closed in x, take this B to be equal to u complement in x. So we have this A is B intersection y, where this B is closed in x. Hence this proves our result. Now let us first define some definitions. So before that, let us define the product topology. So if we have two topological spaces xt and yt prime, so these are two topological spaces, then if we look at this collection, so this B is a collection of sets u cross v, where u is open in x and v is open in y. So this B generates a topology on the Cartesian product of x cross y, and we call that topology to be the product topology. So this product topology has this basis, I mean it contains these elements where u is open in x and v is open in y. So then this B generates a topology on this set, which is called the product topology. Now let us define the open mapping. So let us consider two spaces. So let xt and yt prime be topological spaces. So a mapping f from x to y is called an open mapping if for any open set u of x, its image in y is open. That is, if u is open in x implies its image is open in y, then we call such a mapping an open mapping. Now there is one more definition. So we call a mapping from the Cartesian product of n set, say x1 cross x2 cross through xn to xj, where this j is I mean let us write this. So let us define the let us write the definition like this. So a mapping, say pi from the Cartesian product of n sets to the xj, where j is between 1 and n. So this is called a projection. If this pi takes the n tuple, say x1 through xn, and it maps this n tuple to the jth component of this vector. So where this is called the projection. So this is called the projection of x1 cross xn over xj if this is true. Now we have the following result. So here we define the product topology using two topological spaces. We can generalize this notion to any collection of topological spaces. In particular, we can generalize this notion to the finite set of topological spaces. So this is lemma. So let x1 t1 lemma x2 t2 so on xn tn be topological spaces. So let us consider the corresponding product topology on these topologies like this. So let product of xi, where I goes from 1 to n, be corresponding product space. So that means if we take this set x1 cross so on cross xn and consider the collection B of B of sets which contain the elements of the form u1 cross so on cross un, where ui is in ti for all I, then this collection of sets will form a basis for some topology on this Cartesian product. So that will be our product topology. So this is the same definition which we mentioned here, but this definition was for two sets x and y, and we have generalized this notion to any finite collection of topological spaces. So this is corresponding product space. That means the product topology TP on this space is actually generated by this set over here. This B serves as a basis for this space which contain elements of the form u1 cross so on un, where ui is in ti, where ui is open in xi for all I, where this I runs from 1 to n. So this is the corresponding product space. So what is our claim? Then we claim that the projection map, then the projection map, say pi j from this product space which is from 1 to n of xi to the xj where this 1 is less or equal to j is less or equal to n, defined as pi j takes an element here which is an n tuple, and it maps this n tuple to its jth component. So we claim this projection map is a surjective continuous open mapping. So this is so then the projection map is a surjective continuous open mapping. I mean, by open mapping we mean this map is open status to open status. So let us prove this. So first of all we'll prove that this pi j is surjective. So we have this pi j is a map from x1 cross x2 cross so on xn, which is the product xi. Let us denote this projection map by pj. So because we have two same notations here, I mean the pi and this product. So this is a map from the Cartesian product of these n spaces to the jth topological space. So we have for 1 less or equal to j less or equal to n, we have pj, a map from this set to this set, defined as pj takes the n tuple here, so there is some xj in between, and it takes this n tuple to the jth component of this vector. So this is indeed a surjective map. Why? Because so for any xj in this capital X for any xi in this xj, or let us call this xj here. So for any element here xj in this capital xj, we have an element x1 x2 so on xj so on xn in this product space, such that pj maps this element to xj. So this means this is surjective. Now that means we have x1 cross x2 cross so on xn here, and we have xj here. So if I take any element xj here, for this element there is some element x1 through xj through xn. Now note that there is no restriction on the other components except this xj component. So if I have to exhibit the pre-image of this element, this will be x1 cross so on cross this little xj cross so on cross xn. Now these are capital Xi's and here is a small xi. So to this element we have this as a pre-image. So this is a set over here, and this is an element over here, and note that this element is in this set. So Pj is surjective. Now to prove it is continuous, it suffices to prove the inverse image of every open set is open. Now to prove this Pj is continuous, it suffices to prove inverse image of every open set is open under Pj. So now this Pj is a map from this set to this set. So let us take an open set here, say U. So let U, which is contained in Xj, be any open set. So then P inverse J of U, so that will be actually the product of ui's, where I is running from 1 to n, where each ui is open in Xj. So where if we look at the jth factor of this set here, uj, that is going to be u, and this ui is x for all j not equal to I. So what I mean here, and that is this P inverse J of U is actually x1 cross so on cross u cross so on cross xn. So since there is, so if we look at here, this is the product here. So this is product of these n spaces. So any element over here is an n tuple here, and we have here xj. So if I look at this little xj, its inverse image is going to be actually the set x1 cross so on this little xi cross so on cross xn, because there is no restriction on because each component under this projection map is going to 0 except the jth component, which is mapped to itself. So the inverse of image of xj will be this set over here, where we have at the jth component this little xj, and elsewhere we have these capital Xi's. So if we replace this xj by this set u here, so it is inverse image is going to be u here, because this projection map is the jth component to the jth component identically. So this P inverse J is going to be look like this. Now we have to prove this is an open set here. Now if we look at the product topology TP, this x1 is open in T1, x2 is open in T2, u is open in Tj, xn is open in xn. So this will be an open set because this is a basis element, because what we claim this basis contain the elements of the form u1 cross u2 cross so on cross un, where ui is open in xi. So since xi is open in since xi is open in or we can write this like, since xi is in ti for all I not equal to j, and this u is open in xj, i u is open in tj, we observe that this p inverse j u, p inverse u is an open set in the product space. So this means this p is continuous, p inverse j. So hence p inverse j, not p inverse j, I mean this pj is a continuous map, since it pulls back open sets. Now finally, to prove it is an open mapping, let us take an open set here. So let u1 cross u2 cross so on cross uj cross so on cross un be an open set in the product space. Then pj of this open set here now, since pj is a projection, it maps each component to 0 and it maps uj to uj identically. So this is uj. Obviously uj is open in xj, so that means it maps this open set to the open set, i.e. pj is open mapping. So since uj is open in xj, we see that this pj is an open mapping.